Welcome to lecture 33. So we are going to continue with our discussion on material symmetry. Okay, so we saw yesterday, for example, that the symmetry requirement or the symmetry group G is the following set. It consists of all H such that determinant of H is equal to plus minus 1. And this restriction only the determinant of H be equal to plus minus 1. So the set of all such matrices, it forms a group, and that group is called unimodular group. Unimodular means unit. Its mod is 1. So this is not just the requirement for symmetry group. We further want that the response function for the Cauchy stress, for example, which we denote by sigma. So sigma hat of F is equal to sigma hat of Fh. Either this, or in terms of energy, you can say psi is equal to psi hat of Fh. And we also showed yesterday that both are equivalent. And this has to hold for all F such that F is greater than 0, right? Because it has to correspond to a continuum mechanical deformation. Okay, so this was the definition of our material symmetry group. And we had yesterday started touching upon isotropy symmetry group, right? So isotropy symmetry group is the one in which G contains all the orthogonal tensors. Okay, both proper rotation as well as improper rotation, right? So I can just write that here, that for isometry group, this G is equivalent to what is called O3. So O3 is for orthogonal group. Okay. And there is of course something called SO3, that is called spatial orthogonal group. It's a name in mathematics. It's a formal name. So orthogonal group is such that determinant is equal to 1, and here determinant can be both plus minus 1. So orthogonal group only contains rotations, whereas, orthogonal group contains both rotation and improper rotation or reflection, whereas spatial orthogonal group contains only rotation. Okay, and the isotropy group, I write isometry, should have been isotropy. If it's an isotropy group, then the group contains all orthogonal tensors. Okay, which has determinant equal to, okay, I wrote it here also again in reverse, determinant equal to plus minus 1. And for a spatial orthogonal group, determinant is just equal to 1. Okay, so we had seen that we started with the energy for the thermoelastic material. We had this Helmholtz free energy, right, as a function of big F and also theta, but we'll forget about that theta for now. Okay, and then we could see that this is equal to some Q times F using material objectivity, okay, MO for material objectivity, which had implied that this would be equal to psi hat and some function C. But further, if you use material symmetry for isotropy group, okay, then the psi hat is a function of q c q transpose, where q has both rotation as well as reflection. Okay, so you see it is putting extra restriction. So how should this psi hat look like so that whether you pass C to it or you pass QCQ transpose to it, it should return the same result, right? That is what symmetry group is saying us, isotropy symmetry group. So that means the psi hat must be depending on C in some special way. Or perhaps this psi hat must be depending on those combinations of C which remain invariant when C changes to QCQ transpose. Okay, so this I'll just write here, psi hat must depend on those combinations of C which remain invariant when C changes to QCQ transpose. Okay, so can someone think of what are those invariants? Okay, determinant. So Nikhil says determinant and trace of C. Yes, that is very good. So you can show, for example, this trace of C, which is the sum of the diagonals, no? So that's CII, whereas trace of QCQ transpose, that is going to equal to QIK CKL and Q IL. Yes. But then Qik into Qil, Q being this orthogonal matrix, that's delta KL. So this is same as delta KL CKL. It is same as CLL, right? So you see here CLL and here CII, both are same. So that means trace remains invariant. Likewise, if you think of the determinant of C, or maybe I should find determinant of QCQ transpose, that's going to be same as determinant of Q into determinant of C into determinant of Q transpose. But determinant of Q is plus minus 1. So you get plus minus 1 into det C into plus minus 1, right? Which is equal to det C. So you can see the determinant is also invariant. Can someone think of any other invariant? You remember from your strength of materials class, there are things like stress invariants. And you had similar things over there. So there is another invariant. There were three stress invariants. So there also the stress matrix was changing in this particular way, Q sigma Q transpose. And we are looking for the invariants. So what was the other invariant? Can someone recall? So this is also called I1, invariant 1. Whereas this is called I3, invariant number 3. Okay. And we are missing the second one. So that's I2, and it's equal to half of trace of C whole square minus trace of c square. Okay. So these are the three invariants. You can have some more invariants, but then they will turn out to be, dependent on these three invariants. So these are the only three independent invariants. So symmetry, basically, from mathematics, you can then show that these are the only three independent invariants, and therefore this function psi hat must therefore depend on I1, I2, I3 for isotropy symmetry group or for isotropic materials. Okay, so you see, starting from psi hat being a function of f, which has 9 components, right? So we are starting with psi hat, which has 9 independent components. We have come down to psi hat being a function of just 3 arguments, I1, I2, I3. So that simplifies the functional form, no? Dependence on only 3 arguments. So that's the advantage of using objectivity and isotropy. Okay. Now, having done that, you can recall, suppose I have this psi hat given in terms of I1, I2, I3. You have that function somehow known to you. Then what will then be the formula of first Piola-Kirchhoff stress tensor or the Cauchy stress tensor? Right? So that first Piola-Kirchhoff P was equal to 2 times rho naught into F into del psi hat by del C, isn't it? And here you will then have to use chain rule, and you can say 2 rho naught into F into del psi hat by del II into del II over del C, where I goes from 1 to 3 here, right? Likewise, for the Cauchy stress tensor sigma, that's 2 times rho times F into del psi hat by del C into F transpose, right? So this then becomes 2 rho F del psi hat by del I into del I by del C into F transpose. Okay. Now each of these, del psi hat by del I. This is going to depend on what's the actual functional form of psi hat in terms of I1, I2, I3, right? We have to know this. But otherwise, rest all are kinematic quantities. For example, this thing is something you can actually find out using kinematics. But del psi hat by del I, those three derivatives, you have to know the actual functional form of psi hat. So we haven't yet gotten the actual functional form of psi hat, but at least we could say that psi hat only depends on those three arguments. Okay. So let us see what will this del I by del psi, sorry, del C, for example, will be. So here we have to know the actual functional form. And about this, I said that it's a kinematic quantity, and hence it can be found out, which we will do now. So it depends on kinematics. So for example, suppose I want to find out del I1 by del C. So again, since we don't know how to take the derivative with respect to a tensor, you simply find out with respect to component first, right? That's the trick always. So find out what will be del I1 by del Cij. Okay. So del I1 is del Ckk over del Cij. So what do you think? What is this going to be? So this, of course, if C were not symmetric, you could have written it as delta Ki plus delta Kj. Sorry, into delta Kj. My mistake. Delta Ki into delta Kj. And because of C being symmetric, you have to do this derivative in a slightly careful way, which I have covered in my last class. But this, it turns out, this is what it will be, even for symmetric C. Now this is same as delta Ij, isn't it? Is summation over K, so K can be replaced with any of the two, I or J, and you get delta Ij. So del I1 by del Cij is delta Ij. Then what can you say about the tensor del I1 by del C? Isn't that the identity tensor, right? So this is what I was saying, that these derivatives are purely kinematics, based on kinematics, and you can find it. Likewise, you can show that del I2 by del C, just reverting back to indicial notation, working out the derivative and coming back to tensor. If you do that, you will see that it becomes I1 into identity minus C. Okay. And finally, for the third one, for the determinant, del I3 by del C. So this turns out to be I3 times C inverse. If C were not symmetric, no, it would have been C inverse transpose. So I should write here it is C inverse transpose, but because C is symmetric, it is same as I3 times C inverse. Okay, so that comes from the formula for the derivative of determinant with respect to component of the matrix. Okay, once we have found them, we can then plug it back in the formula for sigma, for example. Let us see what we get. So that means sigma is then 2 rho times big F into del psi by del I1. And I'll use, for this I will use a shorthand notation. I will say it is psi comma 1. That means derivative with respect to first argument, psi comma 1, into identity times F transpose plus psi comma 2, and okay, F transpose is anyway common to every one of them. So psi comma 2 into del I2 by del C, which is again I1 identity minus C, plus the third one psi comma 3 into I3 times C inverse. and this gets multiplied with F transpose. Okay, now we can, combine the terms wherever possible. So you can see that this is proportional to identity and this term is also proportional to identity. So you can bring them together and it then becomes 2 rho times psi comma 1 plus psi comma 2 times this I1 into F transpose. Okay, now coming back to now you have to look at this one. So you get minus 2 rho F into C into F transpose. Okay, and then the last one, the plus sign, 2 rho F into psi comma 3 into I3 into C inverse into F transpose. Okay, now we can further rewrite it as, keeping all the scalars together, it becomes psi comma 3 into I3 into F into C inverse into F transpose. Okay, and then finally we can do some, we can see carefully this. For example, it is F and C is F transpose F, right? Into F transpose. So this is same as FF transpose. You remember it is B, left Cauchy green tensor. So that is B square. Here also you get B. Okay, and what about this one? What is this? Let's try to see. If we expand, then it is F transpose F inverse is F inverse into F transpose inverse into F transpose. So you can see this is in identity and this is also identity. So this is simply identity. Okay, so what you have is then sigma as 2 rho psi comma 3 times I3 into identity. Okay, plus 2 rho psi comma 1 plus psi comma 2 into I1 into B, and then the last one minus 2 rho B square. Okay, I hope I haven't made a mistake here. Yeah, I think I made a mistake. You see this psi comma 2 and then this is inside the bracket. So with C also you get a psi comma 2. So here you have a psi comma 2 also. So you get psi comma 2 in the end. Okay, and same thing, finally you can write it as some constant, let us say alpha naught as a function of I1, I2, I3 times identity plus some alpha 1 as a function of I1, I2, I3 times B plus alpha 3 as a function of I1, I2, I3 times B square. So you can, I have just rewritten it. But basically we just need that function psi in terms of I1, I2, I3. So if you know that, then you can find out the formula for the Cauchy stress. Okay, I think this is clear to everyone. Likewise, one can also find out what will be the formula for the first Euler-Kirchhoff stress tensor, or let us say second Euler-Kirchhoff stress tensor. Proceed further, and I'll just like to make a comment, that for usually for isoelastic material, we also work with what is called strain energy function. Instead of this Helmholtz free energy, which is the specific, it's per unit mass, isn't it? We work with what is called strain energy density function, which we denote by W as a function of big F. So that is per unit undeformed volume. Okay, this density is per unit undeformed volume. And in that case, and how is this related to your psi hat? So we know that psi hat is per unit mass. So to make it per unit undeformed volume, you simply have to multiply this by rho naught. Okay. And the nice thing about this W is that the Euler-Kirchhoff P, which was earlier rho naught del psi hat by del F, that simply becomes del W by del F, okay, without the need of density coming here. You can just write it as del W by del F. Okay, so that has also its a simplification. Working with W is simpler. All right. So having done that, this was one kind of symmetry. There is another kind of symmetry, which is called transversely isotropic materials. I think all of you are aware of this, no? So the other one is, so what we discussed now was isotropic material, but then you have also transversely isotropic material. So can someone tell me what is this material? Or let us say, what will be the symmetry group of this material look like? So we know that symmetry implies that psi hat of F is equal to psi hat of FH. So what will that H be for transversely isotropic material? So transversely isotropic material basically has a principal material direction. And then you can do rotation about that principal material direction and the property remains unchanged. So it's like, you have this material and it has family of fibers. So if you make a rotation about, this axis aligned with the family of fibers, you see the same property, right? So in the direction perpendicular to the fiber direction or the direction transverse to the fiber, you see the same property. That's why we say it is a transversely isotropic material. So then why we have this name? Because in the direction transverse to principal material direction, properties are same. Okay. So suppose this direction is, if I denote that by, let us say, E, okay, if the direction is E in the reference configuration, then what will be H then? Can someone tell me what will be the H? So H is then all rotations about E, all rotations about E. And of course, we know that due to objectivity, this psi hat only depends on C, and therefore, after using symmetry, this must be something like this, H C H transpose. And to be more rigorous, actually, we should say H transpose CH, but it's the same. And if you put only these H in here, no? So we are looking for invariance of C under this transformation. But this H is now restricted. It's not all the rotations. It's only those rotations which are about the axis E. So can someone tell me what will be the invariance in this case? Will I1, I2, I3 still be the invariant under this transformation? What do you think? Remember that I1, I2, I3 was invariant under the big set of rotation for all rotations about any axis. So about this fixed axis E, will it remain an invariant? Yes, very good. So they are still invariants, but you get two more invariants because the rotation is restricted, no? So you get extra dependence, you get extra arguments. Okay, so it turns out you have five invariants, five independent invariants. So you can say that the psi hat depends on five of them, I1, I2, I3, and then I4 and I5. So there are two of them are extra. First three are the same as earlier. I4 is given by trace of C square of E tensor product E. Okay, and I5 is given by trace of C times E tensor product E. So this is what it is. What is this trace of C E tensor product E, for example? What is this? If we try to work it out in indicial notation, we can find out something. So this is same as trace of CE together tensor product E. And then this being trace, here you have a vector and then it is dyadic product or Kronecker product or tensor product with another vector E. And if you want to get a trace, then it's simply the dot product of the two. It is same as CE dot with E. And can someone tell me what is this quantity CE dot with E? When we were doing kinematics, when we were trying to find out strains, what was this equal to CE dot with E? Can you relate it? Anybody? So isn't this the formula for the stretching of the material lines along E? So this gives you stretching square of material lines along E. So what this tells us is that this I5 has got a physical meaning. It's the stretching of the material lines along E. And that's also an invariant under this transformation. Okay, and what about I4? What's the physical meaning of I4? So this is something I will, leave it to you to figure out the physical meaning of I4. And this could come in, let us say, quiz or in the exam. Now to find out again the formula for the Cauchy stress, once the psi hat is known, You can do the same trick as for the isotropic material and find out the formula for the Cauchy stress, right? For example, this sigma would be 2 rho F del psi over del II into del II over del C into F transpose, isn't it? Where I goes from 1 to 5 now. So again, we have to find out these things, no? And we already know it for I1, I2, I3. So we have to think of what will this be for I4 and I5, right? So I'm again going to leave this to you as an exercise. And you might have to derive it sometime, let us say in the quiz or in the exam. So del I4 by del C, so this turns out to be A tensor product CA plus CA tensor product A. Sorry, this is E, no, not A. So again, you have to use indicial notation, all right? And then you'll see that it won't be difficult to work out. Whereas for the fifth one, del I5 by del C, that will turn out to be very simple E tensor product E. And once you have this, you can put it in this formula and find out the formula for Cauchy stress in terms of these derivatives. Okay, and that again, I'm not doing it, but it might come in the exam. So I'll just make that remark here. What will be its expanded formula? Okay, any questions so far? So we dealt with two kinds of symmetry. One, the isotropy, and the other one, transverse isotropy. We know that there are many more, right? Like orthotropy. Then there's something called cubic symmetry. For all those invariants, sorry, for all such symmetries, you get different invariants. And the energy will then depend on those invariants. Okay. So this was, let me proceed further and talk about, how will the constitutive function look like if you have constraint in the material. So this topic is called materials with internal constraint. And this is discussed in chapter 8.6 of the book. So what are the different kinds of constraints that is possible? You can have a constraint, for example, that as a material undergoes motion, it remains rigid. It's a rigid body motion. That is one constraint. Or it could be that as the material undergoes motion, it remains incompressible. So incompressible motion. Or it could be, some kind of inextensible motion in one particular direction. The material is not extending, not stretching. Okay. So what will then be, the constitutive function in that case? Will it be exactly same or will there be something more? So it turns out the constitutive function will have something more. You don't get it completely through psi hat. So basically, in such a situation, you can't, for example, say that P is equal to rho naught del psi hat by del F. That's not correct. Whenever you have constraints in the material, you will have something extra also, rho naught del psi hat by del F plus extra constraint term. And this extra term will be such that it's only this part which is coming from the constitutive function, that's called active part, which is work doing, which does work. Whereas this part, it's called inactive part, does not work. It does not do any work. And do you remember the definition for work or the power? It's P double contraction, for example, F dot, isn't it? Or J times sigma double contraction D. So the extra constraint term, when double contracted with F dot, should be 0. Okay, so that is something which does not come from the entropy inequality. Entropy inequality only tells us this part of P, but this part of P cannot be determined from entropy inequality. Okay, let us now try to explore how will that part look like. Okay, so thinking in an abstract way, we can say that the internal constraint could be given by some function of f. For example, that function could be phi hat of f being equal to 0. And then the actual formula of phi hat will depend on what kind of constraint are we dealing with. For example, if it's a rigid body motion, so for rigid body motion, phi hat of f would be the following. So this function phi hat could be a scalar, it could also be tensor. In this case, it's a tensor. So F transpose F is equal to identity. Isn't this? That is going to happen when you have rigid body motion. That means C being equal to identity. This implies there is no strain developing in the body, right? So that's the constraint for rigid body motion. Then if you talk of incompressible motion, sorry. So in that case, you will have a scalar constraint phi of f, which will be equal to, the formula is det f minus 1, isn't it? The formula of phi f is det f minus 1, and that has to be equal to 0. That's the constraint for incompressibility, isn't it? Similarly, for inextensibility, let us say inextensibility of the material along some direction E. So in that case, the scalar phi f would then be fe dot fe minus 1, isn't it? And these, so these were three specific example, okay? But then you can have any general kind of constraint in the body, which will be given by this phi f equal to 0. And understand that this constraint should also satisfy objectivity. So this function phi f should be such that it is equal to phi of qf. So that simply implies that this phi must depend on just c, right? Phi of c equal to 0. So instead of saying that phi of f equal to 0, you can work with phi of c being equal to 0. And you can notice that each of these actually is dependent on only c, isn't it? For example, first one you see f transpose f is c. Determinant of f is same as determinant of u, which is equal to square root of determinant of c. So again, depending on c, this is square root of determinant of c. And this thing is again c e dot e. So you can notice that each of these three specific cases are indeed depending on the right Cauchy Green tensor, as I mean it should have depended, because it has to be compatible with objectivity. But even for general constraint, this phi hat will just depend on C. Okay. Now, how to find out, the basic question, what will be the extra term in the formula for sigma, or, the first pk? So let's think of for sigma, for example. So for sigma, you will have one term coming from constitutive, coming as a constitutive function, which would depend on, let us say, f. But then you have an extra term, the which is called the inactive term, right? It's the inactive term. And we want to figure out how will that look like. And this inactive term, because it is not doing any power, so it must be such that, so this n must be such that n double contraction d is equal to 0, right? Because the what is power? It is sigma double contraction d, no? So n double contraction d must be equal to 0. No power. Now let us, look at this constraint function phi hat and take its time derivative. Phi hat as a function of c. Let's do it d by dt. So this is then going to be del phi hat by del c, and then double contraction c dot, isn't it? And c being f transpose f, then c dot is f dot transpose f plus f transpose f dot. Okay, and this you can show that it is same as 2 times f transpose into d into f. Okay, that is not difficult to show. All right, so you can then rewrite it as del phi hat by del c double contraction 2 times f transpose df. And this you can further write, if you use indicial notation, you can show it that this is same as 2 times f into del phi hat by del C into F transpose double contraction D. Okay, and since phi hat of C is equal to 0 all the time, its d by dt should also be equal to 0 all the time. So this is also equal to 0. Okay, and if I now compare these two, can you see that n when double contracted with d is equal to 0? So in sort of way n is perpendicular to d, and from the below this thing is also perpendicular to d. So we can actually relate, no? We can say that n is then some scalar multiple alpha times f into del phi hat by del c into f transpose, isn't it? So that's how we get the sigma. So basically sigma is then one coming from constitutive, one term from the constitutive argument, and the other non-reactive term is then alpha times f into del phi hat by del c into f transpose. Okay, is that clear to everyone? Okay, I think I have to stop here. It's already 9:01. But we'll continue from here, okay, in the next class.
So this d by dt of phi hat of C we have written in double contraction form. How that has come?
Yes.
I missed that point. Like d phi by dc double contraction with C dot we have written. So how this LHS
Yes.
is written?
You mean this term, how this is coming?
Yeah, d by dt of phi hat of C. So how we are changing into the double contraction form?
Okay. See, that is, I mean, we have simply used chain rule. That's del phi hat over del Cij into dCij by dt, right? Chain rule, because phi hat is a function of C and I want derivative with respect to time. So we have to use chain rule.
Okay.
And this is
Then
then
this is
C.
equivalent to double
Exactly.
contraction.
Exactly. Del Cij into Cij dot. And that's same as this.
Okay, okay. And so normally, how do we know that it is not going to do any power? Basically, it is not going to do any work, this inactive part. It's like based on intuition or some experimental proofs are also there based on that we are deciding. Like these kind of constraints when we are putting,
Yeah, yeah,
so that
right,
will not
right. Yeah,
add.
that's a good question. See, first of all, why this extra term is arising? So this is, like a reaction to the constraint. For example, whenever you have a beam, if it is clamped at one end, that end does not move. But when you apply force at the other end, there is some reaction force coming over there, right?
Right.
There can be reaction force as well as reaction moment. But that reaction force, whatever comes, that does no work because that part of the beam is not undergoing any displacement.
Okay.
So the same argument you can think of here. It's in a more tensor sense. At every point in the body, there is one part of Cauchy stress which is coming from the constitutive argument. But there is also another part which will be like a reaction to internal constraint. So
Okay.
it's a constrained term. And always the constraint terms never do any work because it's a reaction to internal constraint. So it will not do any work.
Okay. Got the points.
And other
Same thing
thing,
will.
why we are not able to get it from the the second law of thermodynamics, the entropy inequality. You remember in the entropy inequality we had things like P minus rho naught del psi hat by del f double contracted with f dot. Do you remember?
Yes.
And we said that this term must be equal to 0.
Yeah.
That we could say over there because f dot was arbitrary. But now with constraints, f dot is not arbitrary. F dot must satisfy those constraints.
Understood.
So therefore, you cannot say that the thing inside the bracket will be equal to 0. You can have some extra term also. And again, that extra term, when you double contract with f dot, if that is coming out to be 0, then also it will be perfectly fine, isn't it?
Yeah, that inequality will satisfy even with the addition
Exactly.
of that extra term.
So that's why we have, because f dot is not arbitrary, therefore p does not get fully determined from this inequality. We still have some extra term. And that extra term
Understood.
is, obviously it has to be of this form then, right? That n double contraction d equal to 0, if you're talking through sigma.
Yeah. And
Right.
same kind of extra terms we will get even for first Piola
Yeah,
formulas
yeah,
also,
of
no?
course. Of course, of course.
And sir, for transversely isotropy, when we have written this expression, psi hat of f equals to psi hat of fh, and then h we have written like psi hat of h transpose ch. That how are we writing, sir, the third term when we started the transversely isotropy? Yeah, here,
Yeah,
here. So
because
psi
you
hat,
see, from objectivity, psi hat is dependent on C,
yes,
right?
yes. Uh-huh.
So if F changes to FH, what will C change to? C will change to FH transpose FH, which is H transpose CH. And that's why I wrote this here.
Okay.